Hello, everyone. Can you hear me okay? Hey, we have some people in chat already. That's fun. Welcome. It is early in the morning, or not that early in the morning, but it is December 20th, 2023. And I wanted to take a look at this new Kaggle competition that just came out every year around this time of year. And I was worried it wasn't going to happen because it's getting pretty close to Christmas time. Kaggle usually releases optimization type of problem, which to be honest, I'm not usually very good at, but they have released it this year and I thought we could take a look. So they're usually not typical machine learning type of competitions where we try to fit a model to some real data set. They're more of just puzzles that are posed, and then we have to run some sort of optimization to find the best solution. So usually the way it works is people are using different algorithms to find the optimal solution, and it may be reached that the optimal solution is found. It may never be reached. If it is reached, then the first one to get there, they win. If it's not reached, then it's just the best score wins. And of course, there can be tiebreakers. So in the past, there have been like, there was one with emojis where you had to find the optimal order of packaging items or something like that. There have been like ones that were related to Santa's route, how to optimize his route the best. Hey, what do you guys think of this background? Also, let me pull up the Twitch chat. SA, ooh, thank you, Kazar. Pop this out. Yeah, so there have been a bunch of these in the past. Yeah, I feel like the coffee guy, what's his name, with this background, like the really expensive studio that he runs out of, that's actually just a green screen. All right, so we're gonna take a look at it. I haven't looked at this really at all, so we're just gonna kind of try to learn as we go and not get too overwhelmed, but there's going to be a lot of confusion, which is totally fine, and we'll eventually try to figure out exactly what's going on. By the way, if you're watching over on YouTube, you can switch over to the Twitch channel if you want to join chat. I don't really watch the chat too much in YouTube, so yeah, that's the recommendation if you want to. Also, thanks to ChatGPT Dolly 2 for making the thumbnail that I'm using right now, and also this background. All right, let's get into it. What do you guys think? Can you hear the music? Can you hear me okay? Yes, okay, I hope so. Let's do this. Okay, so now I'm on a green screen. I'm going to go ahead and hide this. Like my screen real estate is really, really struggling these days. Can I just X this out? And then I want to make sure I can pull the chat up. Oh, it says no music. Okay, so yeah, I struggle with this because it says that there's some music pumping. How about now? Second time in a row coming to my stream. How's it going, Rob? Also wanted to thank your videos helped me so much with computer vision project that detected and tracked soccer players live in footage. Nice. That's very similar to my last job where I was doing that for the NFL. I'm glad that helped you. I know my computer vision videos don't get as much views on YouTube because it's kind of a smaller crowd of people who are trying to even do that. But yeah, I'm glad that's helpful for you. I try to explain stuff in my YouTube videos that are just really like, they're basically things that took me way longer than they should have to learn. And if only I had someone to show me a few like little things, it would have saved me a ton of time. So that's kind of my goal with those, is to help people get over that hump of the early stuff, and then of course you gotta work hard to really learn the concept. But yeah, even with my pandas videos, it's like get people to stop using spreadsheets. I was that guy for so long, using spreadsheets for everything, and once you get used to writing a little bit of Python code and you just see someone else doing it, then it kind of opens up your eyes to like, oh, I can do all this stuff, and I want people to be creative. All right, can you hear the music now? And I wanted to ask you if you have videos on scripting and some other videos on simple pricing data. I'm not sure what you mean by scripting. On R scripting. Oh, R scripting. No, I'm haven't done R since grad school. Okay, hopefully the music isn't too loud. All right, we'll come back to the chat in a little bit here. Okay, so this is the, I don't like the chat view here. There's like no good place to put this. I guess I'll just leave it there. So the Santa 2023, the Polytope permutation puzzle. So from the little that I've read, this looks like it's an optimization problem for solving a Rubik's Cube, but also other high dimension cubes. So not just Rubik's Cubes, but I think they give us a bunch of different scrambled up puzzles. You can imagine them like Rubik's Cubes, even though they might be like 5x5s, 8x8s, whatever. And we have to solve them in the most optimal way. So this is, I remember I used to do a lot of Rubik's Cubing. It was kind of a fun hobby that me and my coworker would do at lunch break. And then we got pretty competitive with it. And then I actually took my son to a Rubik's Cubing competition, and he blew me away. He's a lot better than me now. But there used to be these problems where people, or I remember in the Rubik's Cubing community, there used to be like solves that people would try to find the optimal solution to. So they give you a scrambled puzzle, and the goal wasn't to necessarily solve it quickly, but to just write down the moves and the steps in order to solve it in the lowest number of moves. So I'm assuming that's sort of what's going on here. Hey guys. Okay, so welcome to chat, everyone who's here. So they come out with this song. I'm not going to sing it. Deck the halls with polyhedrons. Silly elves have dreadful deeds done. Mixed colors on each side to try and spoil Christmas tide. We need your help to fix our tree before the big man comes to see. Okay, so every year at the North Pole, elves adorn the workshop's big tree with beautiful ornaments. These decorations come in many geometric shapes with different colors and markings on each side. Unfortunately, rogue elves have tried to ruin Christmas. Oh, so there are rogue elves? There's an uprising within Santa's elf community, and have mixed their sides like unsolved puzzle cubes. Now we need your help to make things right before Santa notices. In this competition, you will solve cube-like puzzles in the fewest moves, but instead of the usual cubes, the puzzles come in a variety of geometric shape. This sort of magic is no sweat for Santa, but may challenge your data science skills. The entire workshop is counting on you. Can you help the elves efficiently solve their ornament puzzles? So immediately my brain is going to trying to read a paper on how to optimally solve a Rubik's Cube, or look on GitHub for some existing code, because I'm sure there is some. Okay, but we know that the data is a little bit more complicated than that, and we probably need to read the evaluation and all that to better understand how it's going. Okay, so a permutation puzzle comprises a solution state, an initial state, and a set of allowed moves. Okay, so this is like when you have a scrambled Rubik's Cube, that's your initial state. When you have a solved Rubik's Cube with all the colors on all sides, that's a solution state. And then for Rubik's Cubes, anyone out there in chat have worked with Rubik's Cubes before? Anyone else out there a nerd like me? Oh wait, this is a video. So each of these moves with Rubik's Cubes actually has like annotation for it. Kind of like in chess, how there's like numbers for each square and then you move it. So each like up in an up prime would be if you're holding the cube in this orientation, the top layer clockwise or counterclockwise. And it's same thing for this. There's actually annotation for just moving the middle. But that could also be denoted as moving, you know, if you moved the right and the left at the same time, it's almost the same thing as moving the middle. And there's also notation for rotating the whole cube, but that's more for if you're learning like specific algorithms where you'd want to rotate it. Too much nerd talk here. So basically what I'm getting at is I believe what they're going to give us here is the allowed set of moves are going to be like that. The initial state's going to be the scramble and solution state's going to be all the colors on each side or whatever you want to imagine it being. Solution state, we can call colors. Okay, a sequence of moves. If applying each permutation to the sequence puzzle initial states results in the puzzle solution state, and call this sequence a solution to the puzzle. Okay. So there are many ways you can solve these messed up states, right? And we're trying to find the most optimal way of doing that. Additionally, a few of the elves have discovered that they can rearrange some of the stickers. Oh no, they complicated it. They always do this. So a lot of the times these problems take a known optimization problem and then they add a wrinkle to it so that you can't just go and use the research that everyone has on, or well, you should leverage that. But usually there's a wrinkle in it to make it a little bit more complicated than just the basic problem. Also, then it makes it a lot harder for someone to just find the optimal state right away. Because if, like we talked about at the beginning, this is an optimization problem. So someone could find the optimal state today, like all the best solutions to all the problems that they're giving us, all the mixed up cubes. And in that case, the competition would be over for those people, right? They would have won it. So they're adding this wrinkle. So a few of the elves have discovered they can rearrange some of the stickers on a puzzle instead of applying moves. So a puzzle may also be allotted wild card. In this case, resulting state may differ up to the puzzle's number of wild cards in the sequence still considered a solution. Okay. So I'm assuming for certain cubes that they're giving us, or I'm calling them cubes, even though they're polytopes. I don't know what what dimensions are going to be. But we're going to be given a number of wild cards that it's okay to have that many stickers off. So it's not like just finding the best solution. The overall score of a submission is the total number of moves in all puzzle solutions. The goal of the competition is to solve all the given puzzles in the fewest moves. So there's the thing I like about this is it's pretty straightforward what we're trying to solve. Aside from this number of wildcards thing, like it's easy to conceptualize and visualize in our brains what's going on. The metric is pretty easy to understand, right? So they give us the code for the metric. So this is probably just some checks for error. There's a puzzle class. Oh, so the metric's actually kind of, I'm imagining it's going to be a little bit complicated for checking to make sure the solution is correct. So there's a puzzle class. All the puzzle data class has is the puzzle ID, the number of allowed moves, solution state, initial state, and number of wildcards. Where does it initialize a puzzle? So in order to score it, it takes the solution data frame and the submission data frame. Okay, we can look at this later, but it looks pretty simple. Like, this is not a super complicated metric, and it's nice that they give you the metric, because a lot of times we might want to optimize it and try to make it faster if that's possible, because a lot of times that's what this is. If you're doing like a brute force search for the best solution and your code runs 100 times faster than someone else's code, then you're going to find the solution faster than them, right? Let's see what you guys are saying in chat. Me, what is I am Dickel? What are you saying me for? Oh, me, for probably for when I asked if people do Rubik's Cubes. Advent Cyber Vibes. I'm not the best at solving. What's my personal best on the 3x3? 1.9. No, sorry. What am I saying? 1.9. I was just saying a random number. My personal best was definitely like in the 15s. I never was really sub 10. I never could get sub 10. Let me try to find this. I posted on Reddit. This was a long time ago. No, this is someone else's data with the Rubik's Cube solves. Yeah, these are all way too recent. I'll try to find that though. But I had used a program to time myself when I would do solves. This was like 10 years ago. But and then I plotted it all, and it was like clear how it started going down, and then it plateaued at like 10. Early morning stream. Yes, I'm off work this week, so I can. Are you asked about 3x3 nerds? Yeah. I'm aiming for sub 15 right now. I hit 17 last year, but haven't worked on improvement in a while. Yeah, the tough part with Rubik's Cubes is, I have mine over there. The tough part about it is you reach a point where you just have to really invest a lot of time into memorizing. And then I don't know about you guys, but I reach the point with a lot of my hobbies where I'm like, okay, if I really want to get into this, I'm going to have to invest a lot of time and brain power. And then I'll still be pretty mediocre in it. So maybe that's not a good way to approach things, but yeah. Where's my cube? I was gonna grab my cube, but I think my kids have stolen it. How's work? You recently changed jobs. It's good. I'm working for H2O now. If you check out their my YouTube channel, I have like a video on some of the stuff we're doing with H2O GPT, and it's interesting. All right, submission file. For each ID, the submission file should contain a sequence of moves delimited by a period. Okay. Each move should either be a puzzle allowed moves as given its puzzle info, or else one of their inverses, which allow denoted as a negative. Okay, so that's like in the code cubing community, it's like a prime. So R prime is just like the reverse direction. So negative A would be the moves will apply to the initial state from left to right. Each sequence must solve the problem. All right, let's see the timeline. It ends at the end of next month. Okay, so before we look at anyone else's solution, we should probably just do some data exploration, so not to get too overwhelmed with what's going on. I noticed this though. Already we have some teams making big jumps. So it looks like probably if you just submitted, why does it say join competition? I thought I already joined it. If you just submit the baseline, it's probably going to be around 1 million. The score, I'm guessing, is probably just a baseline submission or the best public notebook. So these people are able to make big strides in improving that just off the bat, which is good to know, because that means that there's a lot of room for improvement. If we do look at the code tab, look at the best public score. In this competition, public score and private score are the same thing. There's like really no hidden data. So it's just who solves it the fastest, who does the best score. Ensemble Santa. So they're already ensembling. Iterative replacement of case successive moves. Yeah, so just to before we get too far into this, a lot of times, like for instance, an optimization problem like traveling salesman problem, where they need to go to various locations and you're trying to find the optimum route for it. You can take that. You could take a solution that you know where they go and they actually travel to each destination, and then you can take a subset, like a smaller area within that route, and just optimize that sub area. And a lot of times that's a valid approach for improving an existing solution. Another interesting thing I learned over the years about these type of problems, and I'm by no means an optimization expert, is that a lot of times you're just taking the best solution and trying to improve it a little bit more by doing things like that, tricks like that, where you're taking a subset and optimizing that. Now, there can be situations where you kind of reach a local optimal solution, and then you need to force your algorithm to jump out of that state and to try something completely new. Like it might be super focused on the fact that it has a good solution in one arrangement, but maybe the actual best solution is to, taking the Rubik's Cube as an example, if you found the optimal solution and it always starts with like a left turn, and you're trying to make it more optimal by adjusting other little things, it might be that the very beginning needs to be completely different, and you'll never find that by doing those small increments. So you also need to like do things to hop out of that local minimum. It's kind of fun once you get the hang of it. So, okay, let's not look too much into other people's work yet and just start a new notebook. And I'm going to share this notebook with you all. Santa 2023 first look. What's it called? Polytope. All right. So first look at the Santa 2023 problem. I am going to save this. How's it work? Because time is precious and you got old. Yeah, I definitely got old. I'm going to look at this, make it from private to public. Let's see if it's done. Private to public. I'm going to save this. I really need to figure out how to get a chat bot that will like say things in the chat, like links to what we're working on and stuff like that. Anyone who knows that stuff who could help me out, I would appreciate that. Join our Discord. All right, so this is the link to the notebook I'm going to be working in. It's only going to show updates when I click update. I got Nightbot. Yeah, I need to update Nightbot to do that. Watch this. It used to do !YouTube. Would bring up my YouTube and Discord, but it doesn't do that anymore. It broke. I can easily... Let's go to Nightbot. Log in. Is this me? Maybe it's because I changed my channel name? Dashboard. What is this? Messages? Yeah, see, uptime. This stuff should work. Dashboard. Settings. Maybe it's because, yeah, it's linked to my old... It's linked to my old account. And if I go into settings... I need to figure this out later. Not a big deal. Modbot again. /mod Nightbot. Nightbot is already a moderator of this channel. Commands. Yeah, it's not going to work because I changed my name. It's okay. All right, so let's look at the data for this competition. We have puzzles info, which I believe contains all the possible moves. We have puzzles and we have sample submission. Let's try to... Let's try to just visualize what we have going on. Understanding the data. So let's read in all the data. Info. So we're going to read the CSV. And sample submission. These are our 3 files that we really need to work with. Let's copy this info path. Let's copy the puzzles path. Because I don't even know how many puzzles we have to solve. I don't know if the sample submission is going to work out of the box. All right, so puzzles shape, info shape, and sample submission shape. All right, so it looks like we have 398 puzzles to solve. Info is 27, so I'm assuming that means that we have 27 types of problems. We have 398 different puzzles to solve. This is an assumption right now. 27 different types of puzzles. And that's about it, because our sample submission is going to be just the different moves in order to solve that problem. If I look at the puzzles and we do puzzle type, value counts on this. All right, so most of these puzzles are 3 by 3. Let's plot this. Horizontal bar. We're going to use a different coloring plot. So the puzzles contain the type. Okay, unique New York. New York. Okay, unique ID. Type of puzzle. Solution state. Initial state. Number of wild cards. So exploratory data analysis of this is pretty straightforward. These are all the things I really wanted to know before trying to dive into a solution. How many puzzles do we have? I think we know that, 398. How many different types of puzzles are there? 27. And then let's do the number. We're going to look at here the number of puzzles by type. And we're going to plot this so it looks pretty and we can understand what's going on. Let's set a title, number of puzzles by type. So actually most of these are just like Rubik's cubes, 3x3, 4x4. And then they have, what's a wreath? It might end up being, I don't know this for sure, but this competition might end up being people finding the optimal solution to these really fast. And then the real problem is just like everyone trying to optimize this last wreath one, because I don't understand what a wreath one is. We're going to have to figure that out. All right, so wild cards. How many? What type of problem puzzles have wild cards? All right, so if we go into puzzles and we look at, if we group by the puzzle type, and then we do num wild cards and do a value counts on this, we'll see the number of, unstack this, fill an A as 0. All right, what are we doing here? We are finding for each of these puzzle types, how many wild cards do they give us? We can do this also as type int. All right. Breaking this up to make it a little easier to read. Let's sort values as 0. All right, so x-axis here is the number of wild cards they give us to use. And then the y-axis here is the, or each row here is the by puzzle type. So most of them actually have 0 wild cards, but you could see them kind of splattered in here. So if we do style, background, gradient, we're going to actually see like a heat map of where all the wild cards sit. So it looks like the 3x3 cube, they give us a handful of ones with wild cards. Wild cards are only even. That's interesting to know. Oh yeah, that makes sense. Because if you're gonna switch, color of a sticker, you have to switch it with some other location. I don't know how to do that optimally. All right, now let's look at the info. So I think this makes sense. Like, I don't understand the initial state. Hey, CodePour, thank you for subscribing. I appreciate it. What do you think wildcard means in this context? So we read about wildcard before. Wildcard means that we are allowed to switch. It gives us kind of some leniency in allowing to switch the sticker location. So basically, for those problems, for these cubes, like these 3x3 cubes, where's 3x3? We're allowed to have 2 stickers that we can at the end just swap. So we don't actually need to solve for the full solution. We need to solve for the full solution with 1 extra swap allowed. I don't know why I keep on saying slop. I don't understand this solution state too. Okay, I guess this makes sense. So the colors are letters here, A, B, C, D, E, F. And this makes sense. So thinking about it programmatically, and just taking the 2x2 cube as an example, because that's easiest to understand. But wouldn't a 2x2 cube just have... I guess it has to do with the corners. The thing is, I don't know if this is really a cube that we're solving. If we're allowed to move these all... Okay, so it's going to probably, in the allowed moves, like move groups of 3 of these at a time, or maybe 1 of them, depending on if it's the center or not. I don't know if they're doing it like a real Rubik's Cube. But we're given this basically we're given this scrambled, if we want to not think about this as, Rubik's Cube at all, and just basically think of this as a problem of, you have this initial state of text, right? And we want it to end up being like this, like a very clean 4 A's, 4 B's, all the way to 4 F's. How do we get from right to left in the least amount of swaps? But there are only a certain number of moves that we're allowed to make. So if we look at the info, if we look at puzzle type, let's just look at the 2x2x2 cube. Does that make sense? Does that make sense though? Sorry to make you repeat yourself. No problem. There's only a handful of us in here hanging out, so. All right, so if we look at this 2x2 cube, allowed moves. I All right, let's try to work on a 2x2 as an example. I'm going to save this, by the way. If you want to look at this code, I'm making it public, so it's right here. You can give it an upvote if you have a Kaggle account, and I'm going to go ahead and put this in the chat. Again. Okay, so allowed moves is a dictionary. I just want this actual value. I think this is pretty print, right? So we're going to find our 2x2 moves. And let's try to print this. That's really not that pretty. Is it because we need to evaluate this and actually make it into a dictionary? Okay, there we go. Maybe the normal print will work fine. Nope, let's do pretty print. All right, so we have this move D0. What does D0 mean? Okay, so let's eval this. So eval just makes it into an actual Python dictionary. So then we have 2x2 moves instead of a string. So if we look at the keys, we have, these are all of our available moves that we can make. F0, 1, R0, R1, D0, D1. So I think this is like in a Rubik's Cube, like a front, a right, and a D, maybe the back or the bottom. I don't know. Do they share their environment to us to give us a move and we get the next state, or we need to develop that part as well? No, I don't think they share. Well, I don't know for sure. I don't know yet. That's a good question. Will there be a VOD available of this stream? I usually just leave these up on YouTube. Yeah, so if you check out my YouTube channel, and I try to make them public also on Twitch. So, yeah, there's my YouTube channel. All right, so there are the keys, right? And then we take an example of F0. And what I believe this does is swap out the positions of certain things with other things. So let's take our example. Let's take this first one, which we know is a 2x2. Hey, thanks for the bit. Or the cheer. All right, so this is our initial state, and we want to optimally switch this to being in the solve state. Or solution state, what's it called? Let's take this as our example. Initial state. All right, I'm going to clean this up again. So this is the keys in the available moves for a 2x2 cube, right? Example data for 2x2. And then we don't really need to print all those moves. Let's look at an example move. So this is example move. So let's call this, let's make some variables here. So sol will be our solution. Init will be our initial state. And number of wildcards is 0. That makes things easier. Okay, so then we also have our moves. Let's just make our moves equal to our example puzzle type and info This is just doing it a little bit more programmatically. So if we picked a different example, we would actually get the correct moves for that example. There we go. All right. Now we have our initial state. We have our solution, which is all A, B's, C's, and we have our moves. Oh. There we go. And we have our moves. What? It switched everything in this whole notebook to Markdown? I don't know what I clicked there. I didn't know that was even possible. Our plot, our little plot here. This. This. There we go. All right, now we have our moves that we can apply to this. I bet someone's already written the code to apply a move. What shortcut was that? Yeah, I don't know. Silenced. Welcome. 2 by 2 by 2. 2 by 2 by 2. Oh yeah, it's a... Wait, this is 2 by 2. Oh yeah, 2 by 2 by 2. Sure, yeah. It's a square. Usually in the cubing community, you would assume it's a square, but yeah, to be fair, it doesn't have to be. It could be like a 2 by 2 by 1. Okay, so how do we apply a move? Let's just try to think this through. What we want to do is take the initial state and we want to split on this. Right? By splitting on the semicolon, now we have an array, and maybe we want to make this a NumPy array. Now we have a NumPy array of our initial state. And let's say convert to NumPy arrays. And then we're going to take our solution and do the same thing. Right? So basically, if our initial state is equal to our solution, now we can do this, and we will see where our initial state actually is already in the correct position. So if we print solution, we can see in this fourth location, we have an A, and our solution needs an A. So that is already correct. But we need all these to be true, which is not true here. So how do we apply a move? How do we apply a move to the cube? Right? That's what we need to figure out how to do. So if we basically take this F0 move and just want to apply it to our initial state, how would we change this? So basically, I think what we would do is we would take init and we would find the index locations of each of these. And let's check to make sure this worked. So we're going to do a really stupid way of solving this to start with, but it's getting hot in here. I'm taking off my sweatshirt. I think this works, right? So what we did was we took our init array and then we applied the move F0 to this. So let's just try to look at this and confirm visually this is doing what we want it to do. We have multiple correct solutions, right? We can have the solved cube in a different position. Yes. No, wait. McEnroy. Let's make sure we have our terminology correct. So we have a solved state, right? There is only one solved state. I guess they're calling it solution state. The solution state, there's only one of. It has to always be like this, with one exception, and that's if there is a wildcard. But let's not think about wildcards yet because that complicates things, and we want to just solve the simplest one possible using num wildcards is 0. So this one doesn't have wildcards anyways. But with no wildcards, there's only one solution state. Then what do they call it? Do they call it a solution? Allowed moves. Yeah, so they do call it a solution. Yeah, so, okay, so to back up a little bit, there's a solution state, which there's only one of, and then there are multiple potential solutions, and a solution is like a path that we take to get from the initial state to the solution state. So, yeah, there are, to make sure that we're using the right terminology, there are multiple solutions. There's only one solution state, with the exception of the wildcard. Is the solution state something like the final state? Yeah, think about the solution state as like a solved Rubik's Cube with all the colors correct on each side. What exactly did I do there to apply the move? So when we're working with NumPy arrays, like the thing about this, if this was a list, if init was a list, we could do this too. We could find the index location of each value in this. So always starting in Python at 0. This would be 0 state. This would be the first. This would be the second. And we could just pull out those values by, like this will be an E, right? But what if we wanted to get the first and the first and the second? We could use slicing in lists, but we can't locate multiple indices. When it's a NumPy array, we can do that. So if we wanted to do like 0, 2, 1 would be DDE. We can do that and it'll give us this answer. That's a nice thing about NumPy arrays. So because the move because our move is just a bunch of indices, basically, it's saying like take whatever state you currently have and then move the indices around to be like this. We can just take the moves and apply that indexing to it. That's essentially what we did here, right? Does that make sense? All right, so let's try to brute. Okay, first thing too, I want to look at solution. If we look at the sample solution for this one, oh wait, we have we can also do the inverse of each of these moves. I forgot about that. So, because we can do the inverse of these moves, how would we apply an inverse move? I don't know how to do that. Okay, so if applying the move is just like this, how do we apply the inverse move? And they don't give us the inverse move. That's not completely clear to me right now. So we're going to need to figure. It's going to be simple, but we basically just need to transform this moves from being its existing location. Like our existing location is just 0 to 23. And then if it's the same, it's going to stay in the same spot. Otherwise, it's going to be, yeah, basically the reverse of this. We basically just we could build those inverse as part of our dictionary that we'll search from. Anyone out there have any ideas how to do that? I think you can arg sort the moves permutation to get the inverse. Arg sort. Okay. What does arg sort do again? Performs an indirect sort along the given axis using algorithms solved by the kind. All right, so does this work? Zero, 1, so those will stay the same. Then this is 8 and 10. Because 19 and 17. 2, 3, 4, 5, 6, 7, 8. Yeah, so this is 8. It's 2. Hey, good job. Yes, thank you. I think this works, ET Watt. Does this... It gives you indices instead of values sorted from low to high. Okay, so this is actually what we're looking for. So this is F0 inverse. And if we apply this to our cube, it should work. Okay, so that's our inverse. A sample solution that they give us is just R1. And then remember there's a dot in between each move. I don't know if this is actually, this solution actually works. Let's test it. Let's go to data here. Just download this sample solution. Submit a prediction. How many did they give us per day? 100 per day. Okay, so the submission limitation is not a big deal. Sometimes that is. Let me go over here. Unzip this. Pull this sample solution in, see if it actually submits. Now, it might just error and say this isn't a good solution. Surprised it takes this long. Oh, I guess it has to confirm each of the solutions is is correct. But we can actually apply these moves. We can apply these moves to our initial state. So for move in moves, we'll copy this initial, call that our cube. I think they have like they've already written the classes that could do these moves. We're trying to understand the problem more, but probably pretty soon here we're going to just need to go and use that code instead of fully going off on our own tangent and wasting a lot of time on this. But if we go to moves R1, this is going to be applied to our cube. And that's going to be our new cube state. The thing is, our moves doesn't have the prime. Yeah, so it's not going to find this negative F1. So we basically have to add our moves to add prime moves. Inverse. These are inverse moves. So if we go to our moves, for move and data in items, we're basically going to take these moves, apply our arg sort to that, and then M is our move type. Then we're going to create a new entry in here, which is our inverse, and it's going to be the arg sort of this. So let's go ahead and do this. Okay, so we can't do it directly. All right, so moves is now like this, and it should have these prime moves, right? Except it's a NumPy array, and this is a list. Just to keep it simple, let's make them all lists. Boom! There we go. All right, so take our sample submission moves, apply them to this cube. I don't think it's going to give us the select. Oh, it did. Look at that. Saw this method from a paper on MAEs. What's MAEs? Bug there, I think. Wrong move iterated. I think this is right? This are sample submission moves. But that does give us a solution. Okay, let's look at see if this solved or this submission went through. Still scoring after 4 minutes. Whew. They should cache the solutions when they're solving, and if it equals an existing solution, then not have to go through the computation of solving it all. A little tip there. Might be too complicated for them to do that. All right, so that was a workable solution. When adding the inverted, you check move the keys. You can check by. It's the wreath taking so long. Oh yeah, the wreath one. We haven't even looked at the wreath one. We're just taking it easy right now. All right, so let's make this iterate and check sample submission for all 2x2 cubes. All right, so in our sample submission, in our info, we have all these cubes. In our, what's it called? In our puzzles, let's query where puzzle type is equal to 2x2x2. All right, now we have just the 30, We'll iterate over each, apply the solution in the sample submission file, and then we'll print the solution. Do any of these have wildcards? No, there are no wildcards in this, so that's good. So all of our solutions should equal, should be correct. So for iteros. So we're going to basically iterate over each of these. We'll have our initial state, we'll call this init, like before. Basically, we want to get, we should make like a function for this. And we've already saved all of our 2x2 moves, so we don't need to actually make this anymore, this moves dictionary, just to do this check. So, let's make a function called apply moves, where we give it an initial state and we give it the moves. What's SS moves? Yeah, this will be the moves. Solution moves. And then we'll return the cube. Right? So we'll apply these moves that we find for each of these in the solution. Now we have our data ID. This is going to be what we'll look up in our sample solution. To get our moves. We need to split this by the periods. And then we need to solve the cube by applying these moves. And our init state. And then we're going to print ID double quotes here. All right, so we're going to print the ID and the solved state. Whoa, what's going on here? Solve state N0, N1, N2? That's a little weird. Is this a different type of... What's going on with ID 20? Why is this not A, B, C's, and D's? Okay, this did solve, so these are correct solutions. Solve state A, B, C, D, E. All right, let's see what's going on here with ID number 20. Puzzles. Okay, so this is still a 2x2x2 cube. For some reason, they don't name them. They're not naming them A, B, C, D, and E. And so on. For some reason, these are values are N, 1s, and so on, but this looks right. Okay, so we'll also assert that our solved cube should equal our so taking semicolons and joining this should equal our solution state. So this should always be true. And this assert did not raise, so that means that the solution state of each of these cubes is what it ends up being when we apply all these moves. Any questions here? Oh, unique colors for each square. That makes sense. That makes sense. Okay, so the problem... I didn't consider that. That's stable zero diffusion. That's a good point. So in some of these situations, we have unique colors per square. Oh. Finding some puzzles may have unique colors for each location, not only for each side. Let's explore this. Let's explore this. So if we look at solution state, we could take solution state here. We can apply lambda x. Right? Oh, I'm applying this to an array, so it doesn't need an axis. All right, so I basically made each of these solution states into a list. Basically, what I want to do is do a PD series on each of these. Does NumPy have an n unique? All right, so this is the number of unique. I can just iterate. I know this is not the most efficient way to do it. What happened here? For ID in puzzles, iter rows. Then we want to take the solution state. Number of unique colors for each of those. And then we can do puzzles loc at the index location. So basically, we just made a new column in this data set. That gives us the number of unique colors. And this can be an integer. Got it? What is in the sample submission? Non-optimal solutions? Yeah, I would hope they're not optimal. I was surprised they actually gave us working solutions. But yeah, non-optimal solutions clearly, because this scored. We can even see us on the leaderboard. This scored much worse than what people have been able to achieve. Like this 497 rolled away. This initial one is 1,200,000 or 1,200,000. All right, so let's do the same thing as before. Group by puzzle type and unique colors. Do a size of this and stack this. If I don't unstack this and I plot okay, it's kind of hard to see like this, especially since there's so many potential unique colors. Let me think about this. I mean, we can always just do it this way, just to visualize it. All right, of all these colors, how many unique color, or of all these cubes, how many unique colors are there? I would have thought that, okay, so most of them, there's 6. So if it's 6, that's like a cube. What about our wreath? Our wreath only has 3. Wow, interesting. 33 by 33 cube with 6, 5, 3, 4 different colors. Okay, so that one's kind of hard to conceptualize, but there's a 33 by 33 by 33 cube. There are 2 of those puzzles with just 6 colors. So it would be like a Rubik's Cube with 33 squares on each side. But then there's also a version where every square has to be in its exact location. So that one's going to be complicated. Why'd you have to go and make things so complicated? Could you probe how much the best solutions are doing by calculating the sum of all non 3x3 cubes and then maybe add 40 moves per 3x3 and guess reasonably? Yeah, that'd be cool. That's a good idea. I like that. Why don't I join the Optiver? Sometimes competitions are just at the point where I feel like I'm too late to join the party. Didn't that one close already today? So if I don't know, there's a bunch of brain power you have to put forward to even understanding these competitions sometimes, as you'll notice right by this stream so far. So if a competition only has a few weeks left, I just know that I'm not even going to understand it in time to get a good solution together. You kind of have to pick and choose like that. Yes, last 8 hours. Yeah, so I don't even think about it. But so what else can we do here? Okay, so let's do what you had said. What your suggestion was, which is basically to let's understand, calculate the score. I know we could import. I'm pretty sure that we can import their official code and not have to. So how do we import this metric? All right, let's see what someone's doing. They're doing, there's already people doing blended submissions. So they're just taking all the top public ones and trying to use those to optimize. I mean, that's interesting, kind of. But I wanted to see how people use the scoring. Isn't there a more elegant way to import the metric? No. Yeah, so all those people are doing, I think, all these top notebooks are doing, they're taking the public notebooks solutions, and then they're going through each of the puzzles and they're finding the best of each. So they're kind of like picking and choosing the best, I think. And then yeah, it's not that helpful. All right, so how do I import? Maybe it's here. Add-ons. Maybe it's here. Not models. Find code help. That's not what I want. I basically want to take their metric and be able to import it. Do I just do this? Add it as a data source? Trying to mount session. Okay, so that doesn't work. All right, this is just something else, someone else's thing. But I know there's a way to actually import this metric into the code. Good morning. Yeah, we're just taking a look, RCS, about this Santa competition that they do every year. So we can do it like the other people did it. We can write this solve.py. Or maybe that's something someone else created. I'm not sure. So this looks like slightly different code. Okay, and then they're running it like this. It is going to take a while to solve. So this looks like it takes data puzzles.csv. Input. All right, so this must have been a function that someone else created to calculate the shortest path. I'm not sure. But it would be nice to be able to calculate this solution, the score. I don't want to do that yet, though. Because that's going to get too complicated, let's just try to do some sort of brute force. With our help from a little chat GPT. So, how can we brute force one of these 2x2 solves? Let's just break down this. I am working on an optimization problem. The problem consists of an initial state NumPy array with the location of with values in certain locations of the array. A solution state NumPy array of the expected solution where I want the array to end up. Moves. These are the moves that can be made to the initial state in order to move it to the solution state. The goal is to find the shortest path of applying moves to the initial state in order to reach the solution. Here is an example of the data. So let's show it an example of our So we'll print our init. Init looks like this. This way it'll know it's a NumPy array. Solution. What do we call this? Solution state. Solution state. We want to do this. Want to do this on a good example. So let's do this. Let's just give it all this and see how well it does. Here's an example of the data. And then here is an example of how the moves look. Where moves can be applied to a state like this. Let's see if it gives us anything. write Python code to do some sort of optimization to find the solution state of given this data. I don't know if this is going to be at all usable. So it's saying to use the A* search algorithm, which is effective for pathfinding graph traversals. It combines features of uniform, cost-effective, pure heuristic. However, due to the complexity of A* and the potentially large space, let's write the Python code for this. We'll start by defining all right, so it's splitting this into an array. It's taking our example moves, which we already have. What's this DQ? A list-like container with fast appends and pops on either end. Okay. So it's actually trying to run this code, which I actually don't like. I want to do that myself. All right, so apply move is what we've already done. Breadth first search. All right, so it's not going to actually work with what, because I didn't give them everything. But let's just try to see if this code will at least give us something. Example data. And this DQ. And apply this. Okay, so let's try to understand what this is doing. It is taking the initial state, the potential moves, which we have more of than what we gave ChatGPT. That's probably why it was failing. Array equal current state and goal state. So this is just checking to see if we have the right solution. If it does, it returns that path. Add current state to the visited stat. All right, it's visited. All right, so it's doing this all within this breadth first search. Okay, yeah, so this is this makes sense, like as a brute force way of trying to find it. If we know that we could find, so basically if we have a breadth first search, we have our initial state here, right? And then we can apply any of the potential moves, which will get us to another branch in this tree. And as you can imagine, this tree is going to get very big, very fast. But what it's trying to do is, instead of doing a depth first search where it would go down each branch until it found a solution, because it could then from here there's going to be 6 different, every branch of these basically has all the different potential moves. Instead of going down one branch until it finds a solution, which might be better just to start with, it's trying to do a depth first search. So the difference between depth first search and breadth first search, there's actually animations that show this pretty well. I want to see an animation. Yeah, I guess there's one way to show it. So with breadth first search, it's going to go Yeah, it's going to go kind of like starting at one point, and then if you think about this as like a maze, it's going to go as far the same distance down each potential path, and then start from the beginning again. So it'll go a depth of 1, depth of 2, depth of 3. So this might take longer to actually find a solution that works, but it's going to find it more optimal. The depth first search is going to actually try to go down the path until it gets to the final state that it's trying to find. And it'll do that over and over until it finds, decides which of those is the best. So different use cases for each. This is not going to work. So let's stop this. Stop it. Are these machine learning concepts? These are kind of just like more optimization. Why put the triple thing in the prompt? Because in Markdown, that's how code is notated. So I think it kind of helps the LLMs to figure out. Is this a competition version of the P versus NP problem? What's the P versus NP problem? It's a major unsolved theoretical computer science problem. Yeah, maybe it's. Yeah, it's definitely it's a problem with a solution that we don't know, and then the creator of this doesn't know the optimal solution, and the creator probably doesn't even know if it's possible for us to find the optimal solution in a reasonable time. You could think about this kind of like a chess, how a chess engine works. The chess engine, if it knew the best move for sure, we would be able to say with absolute certainty that the chess engine is winning or losing the game. But since the chess engine is going down each of these branches, also it's trying out the different branches and seeing who is going to be like leading in if a certain move is made. It doesn't in the amount of branches just becomes exponentially so large that it's impossible for it to completely search that space. It's just trying to get us to the best possible solution out of all these almost infinite potential branches that we could go. Similar with this, especially when we get into these more complicated solutions. So, can you provide just the code for a depth first search similar to above? Don't analyze. All right, so we can also give it a maximum depth to look for. All right, so let's try this depth first search, and let's make the max depth 10 just so it's quicker. Let's see if this works. Where does it update the state? I don't know why it returns the initial state and this. There might be some code, the actual, so one of the ways we could kind of try to solve this is by actually formulating it in a way that we can then just feed to an optimizer that does these types of optimization problems. But usually for me, that involves a lot of reading up on it. All right, so it looks like with our depth first search, it did not find a possible solution to this. Initial state being this. And I think this is also the sample solution where there's just one solution that only takes 2 different moves. So we know there's a solution that's very short for this. Make sure it is this one, DED. Oh, no, it's not. Yeah, so let's try, maybe that was part of the problem. The initial state string. Solution state. So this is the one that we know takes only 2 moves to get a potential solution. We're going to try running the depth first search. I need to also make sure I have all the right moves available. Because it's going to iterate over each of the moves. Oh, let's also do this. Make the max depth 2, because we know that there is a solution that only takes 2. Any other questions, people? We're at the very beginning of this, so... All right, max depth. I don't know if this actually... I like putting some sort of progress bar or something in here. All right, with the max depth of 2, it didn't find the solution, so there's something wrong with maybe our moves. There's something either wrong with the code or with our moves. Oh, wait, why is there F minus minus? This doesn't make sense. This doesn't make sense. Did we screw something up? Let's take our info. Let's take our info and our moves. Maybe I ran that cell too many times, or ran it more than once. So what I want to do is take this, put this down here. We're going to take our example. We're going to start out clean, right? So we now have our moves. Should be right. We have our inverse moves. We have our solution state and our init state, but this should be, we should call it the same way as we do here. Don't need to do this. And then let's do our depth first search. Let's add a verbose parameter here. And then we'll print if verbose print result. We'll print the path and the result. What's the result going to be? Oh, the result is the path. All right. So we'll run this. Again, like this. Turn verbose equals true. Oh, this requires our moves. Okay, so this is not working. Let's go to just foobar. The loop where you add prime moves. In the loop where you add prime moves, 6. Okay, so explore neighbors. For move name and moves. We apply the move. If next state is not in visited, but visited hasn't been created at this point, right? We might need to write this from scratch. Maybe next stream. What do you guys think? What do you guys think? Maybe let's take a little brain break. Quickly just look at one of the good solutions out there. Just a little reminder, if you want to take a look at the notebook that we've run, this one's probably going to fail when I try to run it this time. So all this mamma jamma I'd started doing. I'm going to try to save this solution. Get this notebook. Share it with you guys. How does breadth first search differ from, let's say, finding the shortest path in a graph? So we kind of are trying to find the shortest path in a graph, right? The question is, how are we trying to find that path? What approach are we taking to find that? Because in this animated example that we're looking at, the graph is small enough that, yeah, we can visually see where we're supposed to go. But if you imagine, especially for these bigger puzzles, this graph is going to get absolutely ginormous. So we kind of need to figure out a better way to find the solution. Now, they did give us the initial solutions, which maybe we just want to take and improve on. I don't know. This is the part where I just need to get quiet, think to myself, read some papers, read some existing code out there, read if there's any optimization code out there that can do this. Probably should go to the discussion forum and follow this. This person is just posting the top scores. Santametric. After brief understanding what the data is, using data visualization, come to certain understanding of the Santametric. There are some insights. Permutation. Okay, so they do that to represent all moves. Applying moves. Moves are applied the initial state using permutation operations. Scoring. The score is based on the total number of moves. The thing about the discussion threads nowadays is I don't know who just like copied and pasted a question into ChatGPT. It seems kind of riddled with that. Not to say that person did, but it's a lot of just like, hey, look, I copy pasted ChatGPT. Read my comment. Maybe I can trick some people into giving me a upvote. Is this a reinforcement learning problem? Oh, so some people have used reinforcement learning to try to solve Rubik's Cube problem? That's interesting. Minimal optimal solutions. What's a mathematically minimal optimal solution? So these people are trying to guess, I think, on what the number of moves should be optimal, like statistically. But it's going to be kind of hard to do with these wild cards. Minstrel. Someone's using Minstrel. What has the most votes? A-star algorithm. Okay, that's what ChatGPT said to use. This might be someone's ChatGPT results also. Deal with allow moved. Apply move. Apply a move or its inverse to the puzzle state. Develop a search algorithm. Improve search algorithm. Yeah, there's going to be a lot more exploring that we have to do in order to move on from here. So did you guys have fun? Did we learn something? Is this a Christmas themed? Yeah, it's the Santa optimization problem. They do this every year, usually around this time. What do you think about the number puzzle? Will people find leaderboard success in solving fewer puzzles but more efficiently? They're going to write some diff solutions for each puzzle. I don't know. I think that the optimal solution for the really small puzzles probably will be found early on, and then people will start moving up. But it might be that might be the part of the problem, is figuring out where to spend your time trying to find the better solution. Like what's going to give you the bigger bang for the buck. Hello, what am I doing? I don't know what I'm doing. Now we're looking at a Kaggle competition. So it was a fun session. Yeah, thanks for hanging out. I know these live streams aren't as condensed and like they're more just stream of consciousness from me, but I hope that's helpful to some people and that it's enjoyable. If not, you don't have to watch. I'm going to try to also make some more cleaner videos that are actually edited on my YouTube channel at some point soon. So yeah, go to my YouTube channel. I'm going to put that into the chat. Let's do that here. No. Yeah, so if you want to check out my YouTube channel, it's right here. Hopefully you're already following on Twitch. Yeah, follow me on Twitch too, Twitter, all my stuff. Actually, all the links are right down here, so just click on those. We'll find someone to raid on Twitch. And then we'll be done here for today. Thanks everyone for hanging out. Software and game development. Study with the Harvard study. Someone doing their doctoral work in Spanish, though. Okay, so not English. This might not be ideal for our... for our audience. Any suggestions out there? OBS plugin.
Way more flexible in terms
Okay.
of how you
Finite Singularity. Let's go ahead and raid him. If you're on Twitch, that means you're going to be going over to his channel.
We're gonna have
We're going to learn something. And yeah, that's it for this. So let's do... I messed this up yesterday, so I always click this button. Raid. Finite Singularity. And we're off. All right, thanks everyone. See you next time. Bye-bye. Bye. You.